Okay, so this next one here. So we want to graph this e to the x function from 0 to 3. Okay, we want to find this area. So we anti-differentiate 2e to the 2x divided by 2. Okay, because of that k value of 2. We anti-differentiate this. We're going to end up with e to the 6 minus e to the 0. Okay, and that works out to be, as a decimal value, I think it's quite big. E to the 6 is going to be a big number. Okay, e to the 0 is 1, so we end up with 402.4 units squared of area. Okay? That y coordinate at x equals 3 is actually quite high. So again, we're just using that antiderivative to find the area underneath that curve. Okay, so for this one here, the derivative is secant squared, so we know the antiderivative must be a tan function. So it's going to be 2 tan 2x. We want to divide by that extra 2 here, and we want to know the displacement from 0.5, from 0 to 0.5. Okay, those 2's cancel out, so we end up with tan 1 minus tan 2 times 0 is 0. Well, that's 0. So our displacement works out to be tan of 1, whatever that works out to be. Okay, if I type that into my calculator, tan 1 is 1.56 approximately. So slope of 1 radian is a slope of approximately 1.56, and that represents the area underneath this curve from 0 to 0.5. So there are some properties to the definite integral, and they basically follow derivative properties. So if we have a constant in integration, we don't differentiate constants, so we don't integrate constants. I can differentiate functions separately if they're separated by plus or minus, so I can integrate them independently with a plus or minus. This one's kind of important in that if we the next one. This one is fairly straightforward. If I integrate from a to b, well, it's the same area, so integration is going to calculate that area. So it's the same area if I go from a to c and stop there, and then start from c and finish off at b and add those two areas together. It's the same as the total area integrating right through from a to b. Okay, so that's pretty straightforward. This one here kind of has some important implications later on. So, but it's a fairly simple idea in that if I'm integrating from a to b, right? So if I'm integrating left to right, I'm going to have an opposite area if I integrate from b to a, or right to left. And algebraically, it's fairly easy to justify, because if I go big F of b minus big F of a, so I'll put my b and a in there. Okay, so I'm going to get some kind of calculation there. Now, if I switch my bounds, notice I get I'll have big F A minus big F B. So if I plug in my A's and B's in here, here's A here and B here. It's just switching those bounds is switching the subtraction. Well, when I switch subtraction, I'm just going to get the same number or the same area, but I'm going to get an opposite sign on that area. Okay, so this area just is the opposite sign. Okay, well, that makes perfect sense. Where this also shows up is this. Okay, now this is a little bit harder to kind of understand, but if I go from A to B, if I go in this direction, my area above the curve is positive. If I go from B to A, if I go in this direction, that area ends up being negative. Although it's above the curve, it's negative. And try to understand it this way. If I start at time 0 and gain some distance, if I go backwards in time, I'm going to lose that distance. So that area should be negative. Okay, so when we integrate left to right, area above is positive, area below is negative. Right to left, the opposite occurs. Okay, so we're not going to get into that too much right now, but that will show up a little bit later on. I've also added a link here, so try out that link, okay, with the Desmos app, okay, and it'll give you a good idea to kind of help visualize what's happening when we're talking about areas under curves.